All right, so let's take a look at this problem here. So we have a block A of mass m1 is on a very smooth table. So it's very smooth means there's no friction. That's the way you want to interpret that. And it's attached to a block B of mass m2 that hangs over the table as shown. Block A is the distance 3d from the end of the table. And block B is 2d from the deck. So this is the deck down here. I guess this is the deck here. And distance d from the tabletop. So this is 3d, this distance here is d. Okay, so that's everything that they're explaining in the scenario. Now, what's the potential energy of block B relative to the deck? So right now they're kind of breaking into pieces. They're asking you to identify what is the potential energy. When you're calculating potential energy, you always want a reference height. When they say relative to the deck, that means our reference height here is going to be h equals 0. Okay? And so our potential energy here is just simply mgh when you're near the surface of the planet. And so for block B, the mass is m2, it's g, and its height above the ground, above our reference height, is 2d. So it would be 2mg, m2gd. Okay, so that's part A. What is the acceleration of the system when block A is released? Now, when you're asking about acceleration, see, we're getting to the point where you've learned a lot of topics, and when you get a question, it may not always be like, oh, this is definitely a work and energy question. So when I ask you about acceleration, there's a couple of things you should be thinking about. You should be thinking, well, I've done kinematics, or I can do it with forces with F net equals ma. Kinematics in this scenario would require some information, require distance for a motion, the amount of time, initial velocity, and stuff like that. It would require enough information. Probably don't have enough there, but we probably can do this with F net equals ma. Work and energy is not conducive to giving you acceleration. We don't usually talk about the acceleration when you're doing work and energy. So we're going to be relying on force. So if we're going to do F net equals ma, then our process is we got to draw a free body diagram. Right? That's how we're going to handle this one. You can try kinematics. You don't have enough information, though, to figure out what it is. Okay, so what are we going to do in terms of... So we're going to draw a free body diagram of this guy. So let's draw a free body diagram of M2. It would have gravity acting... What's the process? We have gravity acting downward. What's touching M2? We got a rope. It's pulling upward on it, called T. And we assume that the tension is uniform throughout the rope because... Again, unless it's stated, we assume in AP Physics 1 that the string is very light, has negligible mass, so the tension is uniform. If it were a very heavy rope, large mass, then we cannot assume that the tension is uniform throughout the rope. Okay, so that's it. And then we want to identify the acceleration. That's the next step in the free body diagram. This thing would accelerate downward. And then we're going to do F net equals ma. Now, I generally make downward the positive direction in this case, or at least the direction of the acceleration, the positive direction. So then if I make down positive, then my net force is going to be m2g minus tension equals m2 times a. Now, I don't know the tension, so I can't solve for the acceleration. So I have too many unknowns at this point to solve for this. So then I might look at the free body diagram. To figure out the tension, I might look at the free body diagram of m1. It has gravity acting downward towards the center of the Earth. Then it has a table touching it, but it has no friction. So it just has a normal force, but no friction with the surface because it's a very smooth table. And then the rope is attached to here, and it's pulling it to the right. And that's the free body diagram. Now, which way is the acceleration? It accelerates to the right with the same acceleration that this guy's going to have. Because the rope, we assume, it's not stretchable. It's the same length the whole time. So when they move, they have to move together. That means whatever acceleration this guy has, this guy's got to have the same acceleration. They got to move together. So when I do F net equals ma in the x direction, only the x direction, right? Because that's the direction of the acceleration. I only have tension acting in that direction. That would be m1 times a. You can then plug that into there to get rid of the acceleration, and we can now solve for the acceleration by moving this over, factoring out the a, and then you can divide it over. So the acceleration is going to be m2g over m1 plus m2. Okay. C, what is the kinetic energy just before it hits the deck? So now I want the energy right at this point down here. Now, I want the kinetic energy of just before it hits the deck. Now, there's a couple ways to do this one. So I could either attempt to figure. I ultimately need to know how fast it's going. So I need to know the 1/2 mv squared there at that point. Now, because we did the acceleration, we can use kinematics to do that. So think about the kinetic energy as simply equaling 1/2 m2 times this v squared. Now I could, like I said, I could use kinematics because now that I figure out the acceleration of the block, I could use kinematics. And let's just use an example of kinematics of how we could do that. We could also do work and energy. Okay, that would be the more traditional way. But like from there to there, if we say down is positive, the displacement is going to be 2d. The initial velocity, we're going to assume it's released from rest. I don't know if they say it in there. Let's just say it's released. Oh yeah, it's released here. Released from rest. So the initial velocity is 0. Final velocity is what I would like to figure out, and the acceleration is m2g over m1 plus m2. Now, I have 3 pieces of information. I want to find this quantity here. So what equation relates those for is going to be this equation. This is the kinematic equations that would relate those 4 quantities. The one that I'm looking for and the 3 known quantities that I have. So that'd be 0 squared plus 2 times a times 2d. So this is a nice problem because I'm kind of using everything cumulative of what we've learned. Kinematics from both force and forces. So that's v2 squared. Just to simplify, that would be 4m2gd over m1 plus m2. And that's v squared. Now, the kinetic energy, I would want to do 1/2 m2 times this v squared times this 4m2gd over m1 plus m2. Now, you could have solved this problem with work and energy, and that would have been fine. m2 squared gd over m1 plus m2. So that's the kinetic energy there. Now, like I said, you could have used work and energy to talk about this conservation of energy in that process if you wanted to, but you know, that's fine. This is what we did for this one. What's the kinetic energy? Block A at the moment reaches the edge of the table. Well, they both are going to be moving with the same speed. So whatever velocity this guy's moving with, this guy is going to be moving with the same velocity. Why? Because the rope, again, is not stretchable. So when they move, they got to move together, right? So the guy has the same velocity. So the kinetic energy there is just going to be 1/2 m1. Same v squared, though. Right, so this would be 1/2 times 4 is going to be, we'll just make that 2 m1 m2 gd over m1 plus m2. All right, E, what is the potential energy of block A at the same point? So again, relative to this reference ground here, what's the potential energy here? Well, he stays at the same height. It's m1, it's mgh, m1g times the h, and this h is 3d. He's 3d above the ground. So it would be the potential energy of A would be m1g times 3d there. That's the height that the block is at. Okay, and then let's look at this last part here. What is the kinetic energy of block A just before it hits the deck? Oh, okay. So what happens is, so what's going to happen now is block A, so this thing's going to hit the deck, and then block A is going to continue to travel. So once this guy travels 2D, you know, like once this, right before he hits the ground, this guy's like traveled 2D away. But then this hits the ground, and all of a sudden, this block is no longer going to move, and then the string goes taut. It's not taut anymore. Why? Because now this thing will keep moving, and so the rope will slacken. So it's kind of like it's pulling down now, but this thing has some speed already, so it's just going to continue sailing, and it's going to go down to here. And we want to know what the kinetic energy at this point is going to be. That's what we're asked about. Well, we can do conservation of energy here for this block because the rope is actually not taut anymore. There's no tension in the rope anymore, so it's not going to do any work. And if we include the Earth in the system, then there's no work done by gravity. There's no other forces acting on it. So when this thing moves through the air, there's no work being done by any external forces. So the work is 0. So that means the change in energy is 0, which means the initial energy equals the final energy. Now, the initial energy is all of the energy the block contains at the edge of the table, okay? And then, so it includes the gravitational potential energy and the kinetic energy. So it has the kinetic energy, which is this part here, plus it has some gravitational energy, like this. And then at the end, it only has kinetic energy, because at the end, right before it hits the deck, okay, it like no longer has any height. The height is 0 above the deck, so the gravitational potential energy is 0. So then by conservation of energy, we set these equal to each other. Now this guy, I'm going to factor out at M1GD just to simplify. This is going to be 2M2 over M1 plus M2 plus 3. Okay, so this is M1GD times 2. Oh, actually, did they just ask for the... Oh, they just asked what the kinetic energy was. Well, it's this total energy. This energy here is going to equal to the kinetic energy. You don't need to solve for the speed. They want to know what the kinetic energy was, because at the end, all it has is kinetic energy. So it's just going to equal this guy over here. So that would be our answer for our energy there. That completes that problem.